Hello everybody. Today we're going to use abstract algebra to solve another famous problem. Namely, given any angle, can you construct an angle using just straight edge and compass whose measure would be 1/3 of the given angle? This is a very famous ancient problem. And it really comes from very natural considerations. As you know, ancient Greeks really liked to construct things using just these two tools, compass and straight edge. And as you know very well from basic geometry, given any angle, you can quite easily construct an angle whose measure is half of that given angle. In other words, given any angle, it is possible to bisect it. So a natural next question would be, well, given any angle, is it possible to construct an angle whose measure would be 1/3 of that given angle? So, given an arbitrary angle, is it possible to trisect it? And today we're going to see that the answer is no. There are, of course, some angles that can be trisected. And I give to you as a challenge to think of an angle for which you can just use the Euclidean tools and trisect it. However, we're going to show today that there exists at least one angle that cannot be trisected using just compass and straight edge. As you already see on the board, we're going to show that you cannot trisect the angle of 60 degrees. And I would like us to sort of pause for a moment and appreciate how powerful these tools that we developed in abstract algebra really are. We already used them to answer one famous open problem: can you double a cube? And the answer was no, you cannot. Now we're answering another famous open problem that stood open for really long time, for millennia. Can you trisect an angle? And again, we're going to give an answer that is no. It turns out that all these tools that we developed, all this terminology of abstract algebra and these theorems turn out to be extremely powerful tools to solve problems. For example, in geometry, that those problems arose much before anybody thought of abstract algebra. So it's kind of a good thing to appreciate how far we have come and what kind of powerful tools we now have at our disposal. Okay, so we're going to show today that it is impossible to trisect the angle of 60 degrees. In other words, if I give you on a piece of paper an angle 60 degrees that I drew and ask you to just take straight edge and compass and using just those two tools to construct an angle of 20 degrees, I claim that you cannot do it. You cannot construct 20 degrees given 60 degrees using just straight edge and compass. So how exactly are we going to go about proving that this is not possible? We're again going to use the Dedekind product theorem. So we start by saying, suppose it actually was possible. So suppose it is possible to construct the angle of 20 degrees, which is 1/3 of that, given the angle 60 degrees, using just compass and straight edge. Okay, if it is possible, then I'm going to do the following construction. I'm going to take a unit length so this length is 1, and as you very well know, all the rational numbers are constructible. In particular, I can bisect this line segment and construct a line segment of length 1/2. So this is going to be 1/2. The next thing I do is I take a compass, put a leg of it here, and widen it so that I can draw a circle of radius 1. So This is a circle of radius 1. The next thing I do is I construct a line that is perpendicular to this and goes through that point. Again, you know also that that can be done using just compass and straight edge. So this line is perpendicular to the line segment of the unit length, and it cuts it exactly in half. Okay, this gives me a point here, a point of intersection between the circle and the line. So I connect these. I connect the point P to the beginning of that line segment, and this of course is also length 1 then. I can just use the straight edge to connect these 2 points. Okay, so a question, what angle did I get here? All right, I claim I actually got the angle of 60 degrees. Why is that? Because note that cosine of 60 degrees is exactly 1/2, which you're supposed to know from trigonometry. And if I look at the cosine of that angle, I get this length, which is 1/2, divided by the hypotenuse, which is 1. So I do get 1/2. So just by looking at this angle, right, just by looking at it without yet knowing that it's 60 degrees, I can compute its cosine, and the cosine is 1/2 divided by 1. So I know the cosine of that angle is 1/2. So that angle must be 60 degrees. Okay, and here comes the crucial point. I said, suppose it is possible to construct 20 degrees out of 60 degrees. Which means now, using this statement, I can use just straight edge and compass to construct 20 degrees. Okay, this is kind of important. I know that it can be done because I assumed it's possible to construct 20 degrees out of 60 degrees. In the end, I'm of course aiming at a contradiction, but if this were possible to construct 20 degrees out of 60 degrees, then I can do it. So that means I constructed this line just using Euclidean tools. So I get a point Q here. Okay, and if I now draw another perpendicular line that goes through Q, I get another point here, R, and if I call this point here A, then I note that cosine of 20 degrees is AR divided by, well, AQ, but this AQ is again the radius of the circle, so that AQ is 1. So 1. So AR is 20 degrees. Okay, but look, I was able to construct the length AR using just Euclidean tools, right? I showed you how to do this. Everything on the picture I showed you how to do. The only step which I didn't tell you how to do was how to get the 20 degrees out of 60. But that was by assumption possible. Our assumption was I can construct 20 degrees from 60 degrees, so I don't need to know how to do it. It's possible. So this is possible to construct, and then by doing perpendicular I get this point. So this length now I constructed. So as we constructed the length AR from 1, we know AR, and hence cosine 20 degrees is a constructible number. Okay, I was able to construct AR from 1 using just Euclidean tools, so AR is a constructible number. But AR is equal to cosine 20 degrees, so that means cosine 20 degrees is a constructible number. So I can now forget about this picture The rest will be algebra. So maybe I'll just continue with the sentence. Suppose it is possible to construct 20 degrees given 60 degrees. Then cosine 20 degrees is a constructible number. By the argument we just did. We just carried out. Okay, doesn't seem like any contradiction so far. So cosine 20 degrees, whatever it is, you can punch it in the calculator and see what it is in its decimal expansion, is a constructible number. Why should that be a contradiction? Well, let's see. So there is a formula in trigonometry that gives you cosine of triple the angle. We get a formula that says this. Cosine of 3 alpha is the same as 4 cosine cube alpha minus 3 cosine alpha. Okay? That's a formula, that's a purely trigonometric formula. Just like there are formulas for cosine 2 alpha, there are also formulas for cosine 3 alpha, and that's such a formula. Okay? So now we're going to take alpha to be 20 degrees. This formula gives us, I can't spell formula, gives us, well, let's see, 3 times 20 degrees, that's 60 degrees. And what's cosine of 60 degrees? 1/2. So the formula gives us 1/2 is equal to 4 cosine cubed of 20 degrees plus minus 3 cosine 20 degrees. Okay, so if I write, so maybe here, so if we denote cosine 20 degrees by, what's a good letter? I already used out alpha, so maybe let's say A. Then we get an equation okay, cosine 20 degrees is A, so the equation is 1/2 is equal to 4a cubed minus 3a. Taking 1/2, actually clearing the denominators and taking to the 1/2 to the other side, we get 8a cubed minus 6a minus 1 is equal to 0. Okay, all I did was just multiply both sides by 2 and then took 1 to the other side. Hence, A, which is cosine 20 degrees, is a root of (8x cubed) minus 6x minus 1, which is a polynomial with rational coefficients. All right. So here's a lemma that we're going to prove in a moment. (8x cubed minus 6x minus 1 is irreducible. Okay, let's just assume this lemma for a second, and I'll tell you how to prove it in just a moment. So if it's irreducible, so assuming the lemma, we get that what is the degree, oh, not alpha but A, okay, let's think about it. What is this degree? The degree of Q adjoint A over Q is equal to the degree of the minimal polynomial of A over Q. What's A? Remember, A is just cosine 20 degrees. Okay, so what is so I need to know the minimal polynomial of A over Q. But I know that A, well, A is a root of this polynomial, and this polynomial is irreducible over Q. And we know that if I have an irreducible polynomial, oh, you say it's not monic, fine, divide by 8 and you get a monic polynomial. So if I look at, so x cubed minus 6 over 8x minus 1/8 must be the minimal polynomial of A over Q because it's irreducible over Q. So that means this divided by 8 is the minimal polynomial of cosine 20 degrees over Q. So this must be 3, right, which is the degree of. So this is the minimal polynomial of A over Q. Okay, so this is 3. So what do we get? We get the following diagram. We get Q, and then we get QA. But what do I know about A? We just said that A, which is cosine 20 degrees, is a constructible number. And the theorem about constructible numbers tells me that every constructible number lies in some extension F whose degree is, do you remember? Every constructible number lies in an extension of Q whose degree over Q is what? A power of 2. So the argument would go like this. As A is constructible, A belongs to F for some finite extension F of Q such that the degree of F over Q is 2 to the n for some non-negative integer n. But what's the degree here? That's 3. And now you see immediately the contradiction. Because the Dedekind product theorem tells me that 3e is equal to 2 to the n. So, by the Dedekind product theorem, we get 3e is equal to 2 to the n contradiction. Contradiction to cosine 20 degrees being constructible, so to 20 degrees being constructible from 60 degrees. Thus, we conclude that 20 degrees cannot be constructed from 60 degrees. Okay, you just go back into back in our argument and see where we made some assumption to which we just got a contradiction. And the assumption was that I can construct 20 degrees from 60 degrees. Using that assumption, I was able to show that cosine 20 degrees is constructible. And then using this trigonometric formula, I know it is also a root of a cubic polynomial. So I got this 3 here. But it being constructible means it sits inside an extension whose degree is 2 to the n. So I get a contradiction by the Dedekind product theorem. The only missing piece now is to prove this lemma. So we need to prove this lemma. So proof of the lemma. So to show 8x cubed minus 6x minus 1 is irreducible, note I cannot use the Eisenstein criterion because this polynomial is not monic. It is enough to show so let's give it a name, f. F has no roots in Q. Remember that for cubic polynomials, it is enough to show that a polynomial does not have any root in Q to show that it's irreducible over Q. How do I know that it has no roots in Q? I use something called the rational root theorem. So the rational root theorem tells me that the roots of any polynomial with integer coefficients can only look in the following way. So let's erase everything except for the statement of the lemma, which we're proving here. So this is a useful theorem to know. Rational root theorem. It tells us this: if an x to the n plus an minus 1 x to the n minus 1 plus dot 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 a1x plus a0 is a polynomial with rational coefficients, but actually such that a0, a1 through an are integers, and alpha in Q is a root, then alpha is equal to C over D, where C is a divisor of A0 and D is a divisor of AN. This polynomial does not necessarily allow me to find roots of any given polynomial. It just allows me to find all the rational roots. So if this polynomial, so going back to the lemma, if this polynomial has any roots in Q, so if alpha, so the only possible roots possible rational roots of f are, let's see, they're numbers of the form alpha equals C over D, where C is a divisor of the constant term. Well, C divides 1. Okay, well, what integers divide 1? It's only plus and minus 1. And what about D? So D must be a divisor of the term at the highest power. So D must be a divisor of 8. So D can only be plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. So what are the only possible roots of this polynomial? Rational roots would be 1 or minus 1, 1/2 or minus 1/2, 1/4 or minus 1/4, 1/8 or minus 1/8. By substituting all these 8 choices into this polynomial, you see that none of them works. By trying them out, you see that none of these possibilities none of these candidates, let's say, these are only candidates, right? None of these candidates is a root of f. Okay, and this shows that f has no roots in the rational numbers. Being a cubic polynomial, it means that it's irreducible over q. Okay, and that was the last piece that was missing in our proof of the claim that 60 degrees cannot be trisected.